we're looking at finding out what the missing values will be. And for what we have in parts A, B, and C of number 1, okay, we have the base 9 logarithm of 7 minus the base 9 logarithm of 10, okay, is equal to, okay, a single term we're going to have in the base 9 logarithm. And now for what we have in the case of the difference of logarithmic terms in the same base, you're going to have converting from subtraction to division. So once we look at what we have in the single term, we have base 9 logarithm minus the base 9 logarithm of 7 minus the base 9 logarithm of 10. And once we put together, okay, whatever we have to be positive, the attachment goes to the top. And whatever we have to be negative, the corresponding attachment is going to go in the denominator. Okay, so the difference between these terms will become the base 9 logarithm of 7/10. Okay, so in taking what we have now, we have for the outcome, so this will become 7/10. And for what we have in the next portion, okay, so for what we have in part B, we had the base 8 logarithm of a missing value plus the base 8 logarithm of 5 is equal to the base 8 logarithm of 55. And you're looking for what we have here. When we say that the blank will be represented by x, now we have looking at what is present. Okay, now if I'm adding terms in the same logarithmic base, now addition will convert to a single term where we have taking the product of the attachment. So this will become the base 8 logarithm of x times 5, or we could say we have 5x. And we have is equal to the base 8 logarithm of 55. And since we have the same logarithmic base for both of these terms, and since we have single terms on both sides, we can just set the attachments equal to each other. So we have 5x is equal to 55, and x will be the quotient as you divide 55 by 5. So we have that x is equal to 11. Okay, so we have for this portion, the base 8 logarithm of 11 is going to be that which will complete what we have for the first term. And for what we have in part C, now we had the base 9 logarithm of 25 is equal to a missing value times the base 9 logarithm of 5. And for what we have in this case, all right, so we have among our properties, now you can say that we have for the base 9 logarithm of 25, you can write coefficients as exponents. And in this case, we have the base 9 logarithm of what is going to be 5 to the x. And for what we have here, now we have the base 9 logarithm of 25 is equal to the base 9 logarithm of 5 to the x. And with single terms in the same logarithmic base, I can just set the attachments equal to each other. So we have that 25 is equal to 5 to the x. And guess what? 25 is both a multiple and an integer power of 5. And in this case, we have 25 is equal to 5 to the second. So we have that x is equal to 2. Okay, so just filling in what we have now and checking. And the result is correct. For number 2, it says to use the property of logarithms or properties of logarithms to expand the logarithm of x over z to the 7th. Okay, and so for what we have here, so you have for the logarithm of x over z to the 7th. Okay, so you have a quotient, and anything that is at the top of the attachment is going to correspond to a positive logarithmic term. So you have, in this case, you have a logarithm of x, and with z to the 7th at the bottom, we have minus the logarithm of z to the 7th. And in expanded mode, okay, we're going to write exponents as coefficients. So we have a logarithm of x minus what is going to be 7 times the logarithm of z. Okay, and so we have log x minus 7 log z. Okay, so we have filling in, we're going to have the logarithm of x, and we have minus, what's going to be 7, times the logarithm of z, and upon checking, and the result is correct. Now for what we have in the third problem, okay, so we're looking at expanding expressions. Okay, so you have a logarithm of the square root of y to the 7th all over x times z to the 3rd. And so just taking what we have here, and I can just rewrite what I have here. So we have for the square root of y to the 7th, I'm just say I have y to the 7 halves. Then we have all over x times z to the 3rd. And expanding, so we have the logarithm, and anything that is at the top, it will be in correspondence to a positive logarithmic base term. Anything that is at the bottom, we have to be negative. So you have minus the logarithm of x minus the logarithm of z to the 3rd, and writing exponents as coefficients. So we have 7 halves of the logarithm of y minus the logarithm of x, and we're going to have minus 3 times the logarithm of z. So, and in taking what we have now, so we have 7 halves times the logarithm of y, we have minus the logarithm of x, and we have minus 3 times the logarithm of z. And upon checking, and the result is correct. For the fourth problem, okay, it says use the properties of logarithms again to expand, and the answer should not have radicals or exponents. So we have in this one for number 4, okay, so we have, again, so we have logarithm of 4 times the quantity of x plus 8 raised to the 5th. And for the cubic root of x squared, I'm just going to write this as a non-integer exponent. So I have x to the 2/3. And we have upon expanding, so anything that is at the top, okay, will correspond to a positive logarithmic term. So we have the logarithm of 4, and we have plus the logarithm of x plus 8 quantity to the 5th, and since x to the 2/3 is at the bottom, we have minus the logarithm of x to the 2/3, and writing exponents as coefficients. So I'm going to have the logarithm of 4 plus 5 times the logarithm of the quantity of x plus 8, and I'm going to have minus 2/3 of the logarithm of x. So we have, looking at filling in, so we have the logarithm of 4 plus 5 times the logarithm of the quantity of x plus 8 minus 2/3 of the logarithm of x, and checking, and the result is correct. For the fifth problem, if I'm looking at writing as a single logarithmic term, okay, so we have here, just looking at squeezing together as a single term. So you have 1/2 of the base 5 logarithm of x. We have plus 5 times the base 5 logarithm of z, and I have minus the base 5 logarithm of y. Any coefficients I have at the front, I can just write as exponents. So I'm taking the expansion in reverse and making into a single logarithmic term. So I have the base 5 logarithm of x to the 1/2, and I have plus what's going to be the base 5 logarithm of z to the 5th minus the base 5 logarithm of y, and putting all together and making it into a single expression. So anything that is positive, the attachment will be at the top. So we have x is 1/2 located at the top, and since I have plus the base 5 logarithm of z to the 5th, z to the 5th is also located at the top, and since the last term is a negative logarithmic term, we want to have the attachment y to be situated at the bottom. So we have, in this case, we have the base 5 logarithm, and again we'll have x to the 1/2. You have times z to the 5th. You have all over y, and checking out. And the result is correct. Now for the last problem, and writing also as a single logarithm. So here we have 1/4 of the base b logarithm of z plus 5 times the base b logarithm of w minus the base b logarithm of y. So converting from coefficients to exponents. So I'm going to have the base b logarithm of z to the 1/4 plus the base b logarithm of w to the 5th minus the base b logarithm of y, and putting what we have here all together. So at the top, again, now we'll have z to the 1/4, and w to the 5th also goes to the top since we're looking at adding, and since we have subtraction once again, y goes at the bottom. So we have, in effect, okay, so we have a base b logarithm. So you have z to the 1/4 times w to the 5th all over y, and checking, and the result is correct.